All right, we're going to be doing problem 1.3 in Griffiths Intro to Quantum Mechanics 3rd edition, where we consider this Gaussian distribution right here, and for part A we want to use equation 1.16, which is this equation, to find out what this constant A is. And this equation is essentially just saying if we integrate the probability density over all space, it has to equal 1. So we can use this property to determine what A is. So let's just go ahead and plug in the probability density. So I'll take A to be outside, and this will be the integral over all space of e to the minus lambda x minus a squared dx. Now we're just going to let z equal x minus a, and then dz just equals dx. The limits of integration don't change. So this just becomes the integral from negative infinity to infinity of e to the minus lambda z squared dz. And this integral right here, negative infinity to infinity of e to the minus x squared dx, is actually equal to root pi, and you can prove this, and I'll actually just prove it real quick because it's not that hard. You can prove this using polar coordinates. So if we let this be equal to some integral I, and we take I squared, which is equal to the integral from negative infinity to infinity of e to the minus x squared dx times the integral from negative infinity to infinity of e to the minus y squared dy, where we can just take this to be any variable that we want. It's just a dummy variable. And then we can combine this into two integrals, into a double integral, from negative infinity to infinity of e to the minus x squared plus y squared dx dy. And then we can actually just switch to polar coordinates. In polar coordinates, we know that x squared plus y squared is equal to r squared, and dx dy is equal to r dr d theta. And for this integral, we're actually integrating over all space, so we will need to change the limits of integration to reflect now being in polar coordinates. So theta in polar coordinates over all space goes from 0 to 2 pi, and r in polar coordinates over all space goes from 0 to infinity. So this just becomes that integral of e to the minus r squared r dr d theta. So now actually we can solve this using u sub. So if we let u equal r squared, then du equals 2r dr, and r dr equals du over 2. Actually, I'm going to let this equal to negative r squared, so then that becomes a negative and that becomes a negative. So that way the, I guess, integration might be slightly easier. So then this becomes, we get a negative 1/2 factor out front. The integral from 0 to 2 pi is the integral from 0 to negative infinity, because when r tends to positive infinity, u tends towards negative infinity. So you have to change that bound. And this will be equal to e to the u du. So this integral is rather simple, d theta. So this just becomes 1/2 times the integral from 0 to 2 pi of e to the u evaluated from 0 to minus infinity d theta. And this is equal to 1/2, negative 1/2, the integral from 0 to 2 pi of e to the minus infinity is 0, and then e to the 0 is 1, so you get a minus 1 d theta. So this just becomes 1/2 integral from 0 to 2 pi d theta, and then d theta integrated is just theta, and when you plug in the bounds, this just becomes pi. So remember that this is equal to the integral squared. So that implies that the integral is equal to root pi. So that's just proving this relationship right here. Just showing where that comes from. So now that we have that relationship, if we add in this constant here of lambda, you can just make the substitution. You can just make a new substitution, and you'll find that there's just going to be an extra factor of 1 over square root of lambda in the answer. So this answer will be equal to a times this this root pi over lambda, which is this integral, and then this has to be equal to 1, which implies that a must equal lambda over pi. And that's the final answer for part A.